So we're now on the second half of the paper, starting off with a thermometric titration, something you've done, which is where you've got a fixed amount of sodium hydroxide, probably in a polystyrene cup. We've got 50 centimeters cubed, and that concentration, and they're titrating two acids against that. So hydrochloric acid, strong acid, and ethanoic acid, weak acid. And as you'd expect, the strong acid, you get a higher temperature change for that reaction. Okay, and you can see the temperature changes on the graph. Now this question really walks you through step by step what to do. Obviously, on your papers, you just had the points plotted, so you needed to know what to do next. Right, it says using the graph, estimate the initial temperature of the solutions. I have to be honest, I was kind of surprised the number of people who thought the initial temperature was that. Okay, something between 22 and 23. There's clearly a line here of best fit. You can extrapolate backwards, okay? And it ends up with this being the initial concentration. And funnily enough, they meet at exactly the same temperature, which is 21.4 degrees C, as the initial temperature for both of them. And you can see, well, those of you who thought that that was the initial temperature, really have to just look carefully at the axes. At 5 centimeters cubed of acid added, obviously there's already going to be a temperature rise, so it had to be lower than that initially. So that was the initial temperature, and you could get away with a range of 0.1 or 0.2 of a degree, above and below that, I think. The next question over here was to determine the maximum temperature. To do that, a little bit harder, I think. Maybe you've forgotten how to do this, but you have to extrapolate the heating line up all the way up and away like so, and you also have to extrapolate back the cooling line, and it's the point at which they meet. What you don't want to do with these is draw a nice smooth curve around the top there. You extrapolate back the cooling line, and you extrapolate back the heating line, or the increasing temperature line, and the point at which they cross is regarded as the maximum temperature. So for the weak acid it's 29.0 degrees, and the strong acid 30.4 degrees. And again, they allowed a little bit of room for wriggle in that one. Question C asks you to work out the concentration of ethanoic acid. Now remember, what you're doing is a titration between sodium hydroxide and ethanoic acid, which react in a 1-to-1 ratio. Okay, it's a monoprotic acid, isn't it? And you first of all need to know how many centimeters cubed of ethanoic acid were used up. So what you do is you go back to your graph, your ethanoic acid graph, and you look at that point at which those two lines meet, which is the equivalence point for this type of graph, and you run it back down to the volume of ethanoic acid. It turns out 26.0, and I haven't got my mark scheme right in front of me now, but from what I remember, I think you get a mark even for working out the volume there. Forgive me if that's wrong. And then from that volume, you have to then work out the concentration of the concentration of ethanoic acid. Right, so to do that, you need to know how much sodium hydroxide you started with, and you can do some sums. There's a couple of ways to approach it. The way that I would have taught you to do it, and the way that I prefer, is simply to do it absolutely straightforwardly, which is work out the number of moles of sodium hydroxide, 50 centimeters cubed, it says in the question at the start, times by its concentration, which it tells you at the start, divided by 1,000, because 50 is in centimeters cubed, gives you that value. Okay, that's the number of moles of sodium hydroxide, and because sodium hydroxide reacts in a 1-to-1 ratio with ethanoic acid, there's also the number of moles of ethanoic acid in 26 centimeters cubed. Concentration equals moles divided by volume. The volume here, just to save time, I've converted it already into decimeters cubed, which is 26 divided by 1,000, and you end up with a concentration of 1.91 moles per litre for ethanoic acid. Okay, so there is another approach to that you might have taken, which is set out in the mark scheme if you want to have a look. And likewise, the approach I've taken here is subtly different to the mark scheme. They've converted, done conversions in a different place to me, but this is just the way that I taught you, so we'll stick with that. Now, the mistake here, so this is, by the way, working out the heat change for neutralisation. and you all know this from GCSE physics at least, but you certainly covered it in chemistry as well. But Q is equal to mass in grams times the specific heat capacity times the temperature change in degrees C or Kelvin, doesn't matter, same thing. Now the thing that people struggled with is realising that the mass that you needed was the mass of all of the water. And the water was 50 centimetres cubed from the sodium hydroxide and the 26 from the ethanoic acid. Both were dilute solutions, so both of those go in to make up the 76 centimetres cubed. All of that water is getting heated up, of course. Multiply that by specific heat capacity of water, multiply that by the change in temperature, from the initial temperature you got over the page here, which is 21.4 up to 29.0, and that comes to 2414 joules. But it does ask you in the question to convert to kilojoules, so there we go, it's 2.41 kilojoules. There we go. And then again, straight from how I've taught you, which is how do you convert that into the enthalpy change per mole? Well, the enthalpy change per mole is equal to minus Q over N for an exothermic reaction, minus 2.41, divided by the number of moles, which you've worked out already up here using this method. That's the moles of sodium hydroxide and ethanoic acid. Gives you minus 48.5 kilojoules per mole. It allowed, I think in the mark scheme, either minus 48 or minus 49 because of rounding differences and stuff like that. And then you've got to think about why ethanoic acid is different to HCl. Most of you got this. Ethanoic acid, you know, is a weak acid and it's partially ionised. Okay, so you got a mark. Nearly all of you got a mark for that. The second mark I thought was really tough to get actually. You need to realise that the reason, let's go back to the graph a sec. The reason the temperature change when you use a weak acid in a thermometric titration is because if you're reacting ethanoic acid with sodium hydroxide and it's not fully dissociated, which of course it's not, you've got this going to the sodium hydroxide wants to react with the H+. But in order to react with H+, this stage of breaking the oxygen-hydrogen bond has to happen first. And for that you have to input energy, and that means the enthalpy change for the reaction is less. Energy's been put in, it's an endothermic process to break this bond. And so you get a less exothermic neutralisation overall. Hopefully I've explained that clearly enough. If I haven't, please do feel free to ask me. Oh, by the way, while I'm at it, because lots of people didn't get that mark, if you've watched this video, can you just send me an email to say, yes, I watched this video. Don't tell others, because I want to see how many people watch the video. I don't really mind if people don't watch it, but if they don't watch it, I'll know not to do it again. If lots of people watch it, I'll know to do this again. So just for feedback purposes, please don't tell other people to do it. No one's in trouble for not watching it. Some people didn't need to. Okay? But just drop me an email if you watched it. Thank you. Question F. Question F is a very straightforward question which lots of people slipped up in simply because they didn't read it carefully. This is kind of a GCSE rates question. You've got curves X and Y obtained when a metal carbonate react with different acids, and you get a volume of gas produced. So gas increases sharply to start with and decreases in volume, so the rate's fast at the start and slows down as you'd expect. And you've got two different situations, two different sets of conditions. It doesn't tell you what the different conditions are just yet. Now the question asks you, explain the shape of curve X. That's all you have to do. Lots of people compared X with Y and therefore lost the marks here. It's really simple. All you have to say was it's very steep at the start because there's a high number of reacting particles, or you've got a high concentration at the start. And then you have to say that gradually the slope decreases, which means the rate decreases because the concentration is going down, and there's a link between rate and frequency of collisions. Okay, I've probably covered that. There's more than one way to get the marks there, but I've covered everything there, I think. So all you have to do is explain that curve, not compare it with Y. But for the last part of question 1 here, what's possible reasons for the differences between X and Y? Well, clearly Y is a much slower reaction. So what's going on? Why might that be? It tells you you've got the same volume. You get not only you've got the same volume of ethanoic acid, but you produce in total half the volume of, it looks like half the volume, certainly less volume of gas for Y as well. So what are some possible reasons? There's lots of possible reasons, but some obvious ones are you've got less metal carbonate, you've got a lower mass of metal carbonate in the second one, or you've got a higher mass of metal carbonate in X, or lower mass of carbonate in Y. Other ones are the concentration is different in Y, so the concentration of ethanoic acid will be lower in Y, both of which would give you a smaller rate, and they'd give you a smaller volume produced. That's it.